see if we can finish it today about the power electronic, or a small part will remain for the next week. Okay, last week we talked about the power electronic. I introduced to you three power converters, power electronic converters: half bridge, full bridge or H bridge, and voltage source converters. We talked in detail about the half bridges and the PWM, how we are going to change the width of the pulses while they keep the frequency constant and do it pulse width modulation, PWM, and how it's impact the currents, how they changing exponentially, and when we can approximate them with the straight line instead of the exponential change that we have there. We were talking about the full bridge last week, that time almost time out. So what we talked about that said it is very much similar to a full bridge, to half bridge. It's two half bridges. In fact, we can consider it and we can treat it as two half bridges, one here and one here. In fact, we have the VA, we have VB, and VL, the load voltage, was equal to VA minus VB. So VL average was equal to VL average minus VB average. Said one way of treating the full bridges is that, for example, put VB constantly to 0. How we can do that? Turn on the G4 and turn off the G3, then VB will be constantly 0. Then we use the PWM for the other one. Put G4 1 and G3 off, we can achieve that goal. Here gives us the positive voltage. If we do it in the opposite way, mean put the G3 on and turn off the G1, put the G2 on and put G1 off, then VA will be 0, and now we can use PWM for the VB, and so we can get negative voltages if we want around the load, across the load. So we was talking about this part, that, and then we came out to an example that time run out. We're in middle of example 2. Said an MRI electromagnetic is driven by an H bridge. The magnet can be considered to consist of 0.5 Henry inductance connected in series with a 2.5 ohm resistance. The DC power source of H bridge is of the voltage 1200 volts. So L here is 0.5 Henry, R here is 2.5 ohm, and VDC is 1200 voltage. Then in part A of the question, it was asked, and we solved this part last week, that assuming that switching G1 and G2 are pulse width modulated with the switching frequency of 120 Hz, the G3 is off, means G3 here is off, and G4 is on, means like this. What should be the duty cycle to result in an average current of 400 ampere in electromagnet? In this case, VB is constantly 0, so VL will be equal to VA, VL equal VA minus VB, VB is 0, so VL average is equal to VA average, and here we do the pole width modulation. It's just like half bridge, two quadrant chopper. So we can use the same idea. We find the average voltage was we have the current, we have the resistance, we find the voltage, and then D is equal to VL average over VDC, and it was 0.833. Any question up to this point? We did that last week. There's nothing new here. I just, for the keep of the sake of integrity, bring them back here. Okay, if not, here we were in solving this part that time ran out. So what are the maximum, minimum, and ripple current under the condition A? Use both accurate and approximate linear formulation. So we said VB is 0, and we draw this last week. Here is the equivalent circuit considering G4 is equal to 1. Show that how this full bridge will be reduced to a half bridge now. We also said that if F switching is 120 Hertz, then T is equal 1 over F switching, the period or time cycle of the switch, and we calculated the T. Then we said in such a situation, the voltage VL is chopped like that. So we have it on for T on and then go 0, and it is equal to VA because VB is always 0. And then we said that the currents are changing like that. When the G1 is on, here is the circuit. See? These are power electronic switches, but you can consider them like a real switches. The difference is that we can't control them with electric signals. When G1 is on, it's like that we have closed that switch, so the circuit shown in orange is we have there. If we never turn off G1 again, this switch is a simple DC circuit. And the current at the very end, L, inductance, work like a short circuit. So the current goes to the value of 1200, the voltage over R, 2.5. And because it's a RL circuit, we have both inductance and resistance. It's exponential. And time constant is L over R. But at T on, we open the G1 and close the G2, sorry. In this case, the circuit will be like this. Here is the circuit, considered like a simple switch. So this time there is no source, there is no power supply in the circuit. We have some inductance that has some initial current. During this time, it starts to discharge its current, its energy, into the resistance of the circuit. If we never turn off the G2 again and let it to be on forever, the current of this inductance will discharge, decay completely in the resistance. It comes to the 0. During this off time, you see, if we haven't turned it off here at this point and lets it to continue, it continue to 0 because there is no excitation in the system now. But again, at T equal T, at the end of the period, we turn off G2 and turn on G1, and it's happened periodically. So instead of they going to the final values at 480 ampere or 0 ampere, they start to repeat it like this, like the shape that we have shown it here. Now we are asked to calculate the accurate and approximate values for the maximum current, Imax, minimum current, and ripple, which is Imax minus Imean. But both accurate and approximate one. Let's start with the accurate one. As I said, it's 2RL. We can consider it as 2RL circuit. So during the on time, I'm talking about this period. During the on time, this period. So for the period T between 0 and T on, for this period, IL change exponentially. The formula for the RL circuit, I hope you remember, but simply is final value. We said this final value is the voltage of the source over the resistance. It's 480 ampere. So the formula will be the final value plus, parenthesis open, then initial value here is Imean, minus final value is, sorry, minus over 2.5, and this part is changing exponential, minus T over tau, where tau is equal L over R. It's equal 0.5 over 2.5, which is equal 0.2 second or 200 millisecond. Let's call this equation 1. Any question here? Is it clear? I hope the silence means yes. Okay, let's talk about the second period. The second period is this off period here. We're talking about this time that VL is 0, the time that G2 is on and G1 is off. The upper switch is off, the lower switch is on, so the VA will be 0. For this period, so this period, for the period of T between T on and T, this time ILT is equal, the final value said if we haven't turned off the G2 at T, if we let the switches remain for what we have in this situation forever, we don't change the situation at T equal capital T, if we let them to remain this forever, the current goes to 0. The inductance discharges fully into the resistance that we have in the circuit. So the current comes to 0 ampere. So the final value is 0 plus initial value is here I max, we don't know I max and I mean, we want to find them, minus minus final value 0, E minus, but this time is not started at 0, start at t on, so t minus t on over tau, the same tau. And now this time is equation 2. And please note that we have greater and less than equal and greater equal at these inequalities. So t on should be correct. The point t on here is here, should be satisfied at the equation 2 and also should be satisfied in equation 1. The reason is that there is no discontinuity in the current. When we have an inductor in the system, the current cannot jump or fall abruptly. That's why T on should be okay for both of them, because you can see there is no jump here for the current at the point T equal to T on. Any question here? Okay. So we derived equation 1 and equation 2. I brought equations here. Now let's see how we can use them to find I max and I mean. So let's put this point at equation 1 and see how we can get from it, because we use the initial point and final point at infinity to find the equation. Now we are going to use this point inside the equation to get new information. So for equation 1, IL at T on, it should be equal to I max. It means I max will be equal to 480 plus I min minus 480 E minus T on over tau. We also can calculate T on because we know the capital T and D. So where T on is equal, dt will be equal to 0.833, it's d multiplied by 8.33 millisecond, will be equal to 6.94 millisecond. So if you put the numbers there, we will have I max is equal to 0.966 I min plus 16.37. Let's call this equation 3 and save it for the close future. We can do the similar thing for t equal tau at this point. For this equation, we mainly use the initial point and the point at the infinity to find the equation. So we use now the t equal to capital T to find new information from this equation. So for equation 2, we can say IL at T, at capital T, should be equal to I min. It means I min should be equal to Imax E minus capital T minus T on over tau. It is equal to Imax E minus, we sometimes call it T off, over tau, where T off is equal to T minus T on, which is 8.33 minus 6.94. It will be equal to 1.39 millisecond. Thus, I min will be equal to 0.933 I max. Let's call this equation 4. Any question here? Is it clear? Okay, can I go to the next slide? Okay. So in the previous slide, we find equation number 3 and equation number 4. It's like two unknown, two equation. Very simple. We can solve it to find I min and I max. So from equations 3 and 4, can say I min is equal to 3098.8 ampere, and I max is equal to 4 of 1.6 ampere. So these are two of the unknown we were asked in the question, and from this the ripple I max minus I min can be calculated simply. As you can see, these are very close to our average value. That's why when we solved this, the half bridge, we said it is very reasonable to assume that current IL is equal to its average, to IL bar. See, it doesn't change very much from 400 ampere, remain very close to that value. Just for the sake that see how much is the error of what we have done, if we assume the IL average to be IL, let's calculate the IL average here. So IL average, it's equal to 1 over T from, because it's a periodic function, we just need to integral over one period, one cycle, IL T dt. But we have two different equations for this interval and this interval. So we break down the integral to two periods. It will be 1 over T from 0 to T on IL T dt plus 1 T over from T on to T IL T dt. So this one is for this period in the purple here, and this one is for the off time, this period here. So equal to 1 over t. In this period, we use equation 1. So from 0 to t on, we find equation 1, which was 480 plus. Now we have calculated the I mean, so we can replace it in this equation. Minus 480 E minus t over t on, sorry, minus t over tau dt plus, so this one here is equation 1. We just have replaced I mean in that equation, and here from t on to t we have 401.6 E minus t on over tau dt, and here is equation 2. We just put Imax in equation 2 that we find out. The rest is just simple math calculation. There is no pointer. Let me just write it fast here. It's t on plus 81.2 e minus t on over tau minus 1 plus 401.6 e minus t on over tau minus 1, and if you calculate all of them you will find 401.1 ampere, which means in comparison to 400 amperes that we consider to be the average value, is less than 0.3% error. Any question? Is it clear what's happening? So everyone is okay with this. Good. Okay, let me go to the next slide. Okay, here is the approximation method. For those of you who are very pragmatic and think just for the exam, I recommend to listen to this part more carefully, though that part was also important. But now this time we said, okay, we said in some cases we can use an approximation, a linear approximation. Anyone remember when we can use such a approximation, that we approximate the change in current linear? What was the condition to have such a simplification? Instead of exponential, this time we have the linear one. What was the condition for that? Anyone? Nope. No one. Okay, so the condition was that the time cycle, t, time period, be much smaller than tau, the time constant of the circuit. So since capital T is much smaller than tau, we can assume that the load current rises and falls linearly with respect to time. And we had an equation, we introduced an equation for you to use in that moment. In general, said delta IL, the ripple in the current, can be approximated with VL, and I emphasize several times that this VL is not the average VL, minus RIL minus E over L delta T was the formula in a more general case. Here, in this case, in MRI, we don't have any EMF or back EMF, so E is 0 for us here, but you may see some cases that you have E. Then you can use this equation. You can use it for both time intervals of off and on time. What does that mean? So you can use it once in this interval, or either you can use it in this interval. Both of them will give you the answer. You don't. Pardon? Why is E 0? Because we didn't have any EMF or back EMF in the load. If you remember, the load was simply an resistance and inductance. If it was a motor, it wasn't an MRI, then you have the back EMF. And here is 2. So you can use either intervals to find the current ripples. So let's do both of them for the sake of completeness, but in most of the cases you just need to do one of them. So for the interval 1, delta IL is equal to Imax, the final value minus initial value, Imax minus Imin. Delta T is equal to T on. See? What is VL in this interval? VL. What is VL? Pardon? Exactly. So it is equal to VDC equal to 1200 volt. Now you just simply need to replace these parameters, these values in the parameters in the equation. So current ripple will be equal to delta IL, which is equal to Imax minus Imin. It is equal to 1200 for the VL minus R was 2.5 multiplied by. For IL, we said we can approximate IL with IL average. We discussed this in last session and emphasized it. So for IL, we use the IL average, which is 400 ampere over L is 0.5 Henry and T on is 6.95 millisecond, but bring it back to the second and it gives you 2.78 ampere. You can use very similar idea for the second interval. So here what is delta IL in this interval? What is delta IL in this interval? It's a very simple question. What is the current ripple in this interval? Can you see the IL curve there? Is it clear enough? So what is the final value of the IL there? Final value of IL in interval 2. Ayman. Minus. What is the initial value? Not you. No, this time. Imax. What is the delta T this time? Delta T.
Minus T1.
Yes. Thank you. What is VL this time? Pardon? 0. Okay. Now I mean minus I max is equal to 0 minus 2.5, and we use IL average for IL. We calculated in the ever given, I believe, in the question. 400 over 0.5 multiplied by 1.39. This is T minus T on, and it's equal to minus 2.78 ampere. For sure it gives you the same answer, just with the negative sign. Said we can use either of them, either interval 1 or interval 2. Both of them can give you the answer. Any question here? Any question? Okay. We still haven't found Imax and Imin, but it's very simple here because the changes are linear. IL average it's equal to Imax plus Imin divided by 2. So Imax will be equal to IL average plus half of the ripple. It is equal to 400 ampere plus 2.78 over 2. So Imax will be equal to 404.4 ampere. What is I mean? No, not here.
Same thing but minus.
Pardon?
It's the same thing
But yeah, yes. So I min will be equal to 398.6 ampere. So we calculated everything that question was asked from the approximate method. And if you go and calculate it, compare it to the values that you find from the accurate one, the error is less than 0.1%. Very close one. In many cases, they can use similar methods to calculate the repos and for the designing concerns. It's very effective. Any question here? Any question? Go ahead.
You said that for the approximation method, the T has to be way less than tau, right?
Yes.
Is there like a specific value of ratio that you can use?
If it's 5 times smaller, 5 or 4 times smaller, that's good to go. Yeah. Okay. Okay. Part C of the question asks, assuming the current has reached the steady state value of the 400 ampere and ignoring its fluctuations, what we have done is we said IL can be approximated with IL average. How fast will it decay to zero if G1 and G2 are suddenly turned off while G4 is still on? So what we are talking about is that we have this current in this direction is at a steady state 400 ampere. Then we turn off this switch, these two switches. G3 was also off before that, but we keep the G4 on. So we said we have an inductor. In this case, we have a very huge inductor. We cannot change the current suddenly. It's not like a resistor. It takes some time to decay. Otherwise, it's going to have some impulse current and many problems. So the current should find some way to flow. So here we have this current in this way. It cannot go through G1 or G2, but it wants to find some direction. If it goes from here, it needs to go, it cannot go through G1 because G1 is off, and its direction, it's opposite of direction of the diode. So this diode cannot conduct it. But if the current comes from here, it's okay. We can keep the current flowing. Let's go through the diode. So the current continues. Now it wants to exit the point B. For exiting point B here, G3 is off, but G1 is on. So it continues through G4. So G3 is off, G4 is on. It has some way to go. So it goes from here and continue like that. So you have a circuit like this, showing with this orange color. Your circuit will be closed. Is it clear why? Go ahead. Oh, it can go, but because the G4 is on, it prefers to go through G on. So if a switch is on, the voltage across it is zero. It's simpler to go through that. It prefers, let's put it like that, it prefers switches. Any question? Okay. So we said G1 is off, G3 is off, G4 is on, and then we have D2, and we said here we will have the path for following the current, IL. Because going through this, because G4 is on, the voltage across this switch, what is the voltage across this switch when the switch is on? We talked about this last week. What is the voltage across the switch when it's on? 0, yeah. What is voltage across a diode when it's on? What is voltage across a diode when it's on? Pardon? No. I'm so sorry. It was so random, I believe. So what voltage across the diode? What is that? It's like a switch. When you turn it on, it's like a wire. The voltage across it is 0. We discussed this about 5 minutes last time in the last session. So voltage here is also, let me put it like this, is also 0. Sorry. Okay. So let me write some point for your future reference. It seems that you haven't studied for this class. Hopefully you will study for your final. Since IL is greater than 0, in fact IL was equal to 400 ampere before the change, just before the change. So it will flow through D2. So ID2 will be equal to IL. When a diode, when a switch, whether a transistor or a diode, is conducting, the voltage across that switch is 0. It's like a short path, short circuit. So VD2 is almost 0. So now that voltage across this switch is 0, what is the voltage of VA? VA voltage. Is it equal to VD2 plus 0? Can you see this 0 here? VA is equal, voltage at A is equal to VD2 plus voltage here is 0. Am I right? What is the voltage of VA so? That 0. Perfect. Can you say what is the voltage of VB? It was so good in this one. Good. For very much same reason, the other switch, the transistor, is also conducting. Voltage across it is 0, and VB is also equal to V across that switch plus 0. See? VB at this point is equal to voltage across this switch, and voltage here is 0. So VL is equal to VA minus VB is equal to 0 volt. So we are dealing with a series RL circuit in which the inductor has some initial current which, in absence of any excitation, will decay to 0. In very simple language, plain language, you can see this circuit that we have here. There is no excitation inside it. This circuit, see? Just we have an inductor with some initial current, so it starts to decay, to discharge through the resistance. And it's a simple RL circuit. So ILT formula will be final value plus initial value minus final value over E minus T over tau. So it goes through to the approach 0 exponentially. It's never cross 0. So IL can be assumed to be 0 in 5 tau plus t equal 5 tau is equal 5 multiplied by 0.2 second equal to 1 second. It takes 1 second for this inductor to be discharged to resistance through the circuits that we have built here with turning on and turning off that we have done. Any question here? Any question? Everything's clear? Okay, because you like this part very much, let's go through another part very similar to this one. This time we also turn off the G4. So what does it mean? Said G3 was off before, we turned off the G1, turned off the G2, and this time we turned off the G4 too. So current, again very similar to that last part, is 400 ampere, cannot change abruptly. It needs to find some path. So current comes here. Then it should find a path. Can it go through the diode of the D4? So it should go this way and continue. Then, so the current is like this. Reach this point, it cannot go through G3, G1, and it cannot go through its diode because direction of the current it's in opposite. So it continue and go through the source. And this is circuit. We need to close the circuit. So it comes back. Now, at this point, it needs to go back to close the circuit. Can it go through the diode of G2? Yes. So it goes like this. And here, like this, the loop will be closed. And then the current will circulate like this. Any question? Is it clear to everyone? Okay, we'll see. So we said turn off G4 and turn off G1, and we said okay, the direction will be like, sorry, will be like this. Now this diode will be on, so voltage across it will be 0. And now this diode is also on, the voltage across it will be 0. What will be the voltage of VB? What is the voltage of VB? Exactly. What is the voltage of VA? VA. VA. You, sir. Which one? Who said? Okay, it's 0 anyway. Okay. So similar to the last part, IL is greater than 0. IL, in fact, sorry, is equal to 400 ampere just before the change. So this time ID2 will be equal to ID3 will be equal to IL. So D2 is on, D3 is on. So VD2 is almost 0. VD3 is almost 0. From this we find VA 0 and VB equal to VDC. So VL is equal to VA minus VB is equal to 0 minus VDC will be equal to minus 1200 volt. It's like that we have a reverse voltage, a negative voltage across the load. So this time it starts to discharge much faster because we have excitation in the system, but in opposite direction. It forced the current to go to 0 much faster. So ILT will be equal to, if it had such a circuit forever, there weren't switches there weren't diodes there, it was simply a circuit, the final value of the current was 1200 VDC over R, but in opposite direction, because now the positive of the source is in the opposite direction. Plus initial value minus final value over E minus T over tau, it will be equal to minus 480 plus 880 V minus T over tau. So in fact, if we try to draw this, we have the T here, we have the IL here. So before T equal to 0, the current is constantly 400 ampere. At T equal to 0, we change the switches. So it start to decay exponentially. If it wasn't diodes, it continue to get the value of minus 480 ampere. But it cannot. Why? Why does it stop at 0? Any idea why it stopped at 0? So after get to 0, the direction of the current change. Can it go still through the diodes? So the diode stops the current at 0. It cannot reach the final value there. To stop at this point. And we need to find this point. It's where it crosses 0, wants to cross 0, reach the 0. So ILT equal to 0. If you solve this, you need to find, in fact, this value, 480 over 880. So T will be equal to 0.6 tau. It will be equal to 0.6 multiplied by 0.2 second. It will be equal to 0.12 second or 120 millisecond. So in fact, this point is 120 millisecond, much faster than part C. Any question here? Is everything clear? Okay. Everyone done writing? Now, we talked about these 4 quadrants. The method that we use up to this point was, we consider it almost 2 independent legs. We put one of them to the 0 and PWM the other one. Said, put the G4 on, keep the G3 open, VB is 0, now do PWM at the other one. It gives you the positive voltage you want. If you want negative voltage, you should do the opposite. You keep G2 on, turn off the G1 constantly, and do the PWM at this leg. Now you can find negative voltage. But can we do it with doing PWM simultaneously at both legs? Yes, we can. I think you already have seen this in your lab and in your tutorials. So suppose that both legs of the bridge are pulse width modulated that includes G1 and G2 in companionship, and G3 and G4 in companionship. However, the duty cycle for G1 G2 pair is D, where for G3 G4 pair is 1 minus D. When we say in companionship, it means we talked about the relation in G1 and G2 to be negate of each other. Put the NOT gate between them. Whenever G1 is 1, G2 is 0. Whenever G1 is 0, G2 is 1. Very similar thing for G3 and G4. That's what we mean with the companionship. So again, we somehow consider these two legs somehow independent of each other. We do the PWM even with different duty cycle for them. One of them with duty cycle of D and the other with the duty cycle of 1 minus D. So let me go to the next slide and put this in more mathematical way and see what does it mean and what will be the result for us. So it said let's put the duty cycle of G1 G2 equal to D. We can write this as dA it's equal to D, means duty cycle of leg A equal to D. So here we know from what we have done for the half bridges, VA average will be equal to D VDC. Similarly, if we put instead duty cycle for pair G3 and G4 be 1 minus D. So in other words, we can say dB is equal 1 minus D. So duty cycle for leg B is 1 minus D. So VB average will be equal to 1 minus D VDC. And we said VA average is equal, V armature or V load or VL average is equal to VA capital average minus VB average. It will be equal to 2D minus 1 VDC. D was T on over capital T. So D always is between 0 and 1. What will be the value of the VA average? What will be the minimum value for the VA average? Anyone? And the maximum one will be VDC. But why we like it that much? Because this time we don't need to go and say, okay, stop the PWM at this bus, keep this leg, keep it constant, and do the PWM at the other leg. And if we want to go to the negative voltage, we need the inverse. It's a continuous PWM at the both legs that is going to happen, just with changing the duty cycle. You change the duty cycle between 0 and 1, and your voltage can change between minus VDC to VDC. Very same idea. You don't need two very different idea of the switching for the legs. So since the load voltage can be varied continuously by varying D, this operation is referred to as continuous 4-quadrant operation. Any question here? Any question? So let's see some simple cases. Assume that D is 0.8. Then G1 and G2 is for arm A or leg A. So dA will be equal to 0.8 and VA will be equal to 0.8 VDC. And it changed like this. Oh, sorry. It's 0.8. And we talk about the companionship, that is exactly G2 is the opposite of G1. So like this. For leg B, dB, what will be the dB here? When D is 0.8, what will be the dB? 0.2. Yep. So VB average will be 0.2 VDC. This time it's like this, like this, this. So we change like this, and G4 is simply opposite of G3. So here is 1 0 1 0 1 0 1 0, and here we have the time t, 2t, 3t, 4t, and 5t for the time cycles. Then as a result, VA average will be equal to 0.6 VDC. So the waveform for VA will be like that, where the T on here is 0.6, the time here is 0.6 T. Now here, because D was greater than 0, greater than half, VA average was greater than 0. Any question here? Is it clear? Is it clear? Everyone done writing? Okay, let's go to see another example. This time D equal 0.33 or 1/3. So here dA is 1/3 and VA will be equal to 1 V capital A, sorry, is 1/3 of VDC. DB will be equal to 2/3 and VB average will be equal to 2/3 VDC. So what will we see here? It will be like this. And here is the time t, 2t, 3t, and 4t. Here is 1 and 0. For the G2, the relationship is opposite of the G1, can simply say it here. For G3, we have 2/3, so we'll change like this. 1 and 0. And G4 is simply opposite of G3. Then if you draw the voltage at the very end, minus VDC, here you will have this. Oh no. As you can see, the negative voltage can be seen here, and VA or VL average is minus 0.33 VDC. So for D less than half, VA will be less than 0. For D equal to half, VA average will be equal to 0. It's the case that you want some installment on your rotating machine. You keep the VA 0 and installment will be achieved. Any question here? So in this case, as you can see, you just see negative voltage and 0 in the negative voltage. In the case of the positive voltage, you saw just positive voltage and 0. That's why in some cases they call this way of switching or PWM, they call it unipolar PWM, unipolar. Just you have just positive or negative and 0. You don't have both positive and negative. But there is another way of continuous switching that I believe you have seen it in your tutorial examples. In that case, they always switch G2 and G3 together and G1 and G4 together. So when G1 and G4 are on, you have this voltage. So what will be the voltage of across the load? Will be positive VDC. See, here is the circuit. When G1 and G4 is on, the voltage across the load will be positive VDC. But if G1 and G4 are off and we close the G3 and G2, then the voltage across the load will be negative, minus VDC. Very similar formula is used here too, 2D minus 1 VDC, but the switching scheme is different. The good thing is that it is generated very easily because we get the D, our duty cycle, then we send it to a comparator that we talked about it with that high frequency triangulars. And then the result will be given to G1 and G G2, and we just negate that, sorry, G1 and G4, and give it to G2 and G3. So, for example, for D equal to 0.33, G1 will be like this. Very similar to what we have done previously. And G4 is the same. So 1, 0, 1, 0. As you can see, G1 and G4 are exactly the same. And G2 and G3 are opposite of G1 and G4. So there are like this. Here, 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 and here. And then 0, 0. The output voltage, the average voltage, will be the same as we find the last time, but it's not, the waveform is not exactly the same. So if we have VDC here and minus VDC here, then it will be very much same relation that VA or VL average is 2D minus 1 VDC. But difference here is that you have two polar. We have VDC and minus VDC. Previous time, if it was a negative voltage, we just have 0 and negative VDC, minus VDC. Or if it was positive voltage, it was only 0 and VDC. But in this method, we have positive VDC and negative VDC in the waveform. For the steady state, the result is the same. For the sake, it average in the sense of average value, very much the same result. But they are not actually the same. In the sense of more dynamic, more transient, in more accurate language, the RMS of value or ripple that they result in the current, they have different result. But we are not going to talk about them in detail in this course. I think we can have a 10-minute break at this point and continue after the break. Okay, let's continue. Up to now, all the converters that, excuse me if you sit in your, okay, take your seat, thank you so much. Okay, let's continue. Up to now, what we have discussed, if you remember, in all of the cases where it was a half bridge or full bridge, the output voltage was always less or at best equal to VDC, the voltage of your power supply, your source that you have. But there are the cases that you may need higher voltages. For example, you are, in an electric vehicle, your battery is giving you 12 volts and you want to charge your something that needs some higher voltages. So you need some converters that can give you some voltages higher than your source voltage. For that, you are going to use what is called as step-up choppers. So let me write a few points here. So the power electronic converters that we have introduced so far provide an average voltage less than the source voltage. Second point is that a step-up chopper aka boost converter, so we also call this boost converter, can provide a voltage higher than the source voltage. And it consists of a switch, a diode, an inductor L, and an output capacitor C. So in this case, the converter is not only some switches, it also consists of a capacitor and inductor in addition. So if you have your source voltage like this, and if you have your load like this, RA, LA, E, here is the load, then your converter is like this. It's L. We have the switch, we talked about it. We have a diode. We have a capacitor. C. Hold this green part all together is a boost converter. We don't have a switch cell here, if you see, just a transistor, and the diode is there. It's not like a half bridge or full bridge here anymore. Transistor, we call it switch with the signal G, and the voltage across it is V switch. Here we have our diode, the voltage across it, it's VD. Here we have the output voltage. The voltage across the load is the voltage across the capacitor, very much the same voltage. Here is the current IA, the current of load. Here is ID, the current of diode. And here is the current of IL, the inductor current here in this case. And here is the voltage across converter. Is everything clear up to now? So now we want to have a voltage, a converter, sorry, to boost the voltage, to give us a higher voltage than the source. And here we have it. It's not simply some switches. It also consists of an inductor and a capacitor. We don't have a switch cell in this case. A transistor and a diode are not anti-parallel together anymore. Okay, if we are good here. We need to make some assumptions to make analyzing this circuit, this converter easier. Otherwise it can get a little bit nasty and hard. So let's make some assumption here to make everything easier. First of all, we assume that the voltage, the current inside the inductor never be interrupted. It's continuous. It never crosses the zero. So one, the current in the input inductor L is continuous that is IL never crosses zero. First assumption. Secondly, we assume that capacitor C is large enough so that the voltage VA is constant. A constant DC voltage. 2. The output capacitor C is so large that the voltage across it which is the same voltage as the load voltage is constant and ripple free. So V, in other words, VA is equal to VA is equal to constant. Now that VA is constant, it's like that we have a DC circuit there. So IA will be constant. The current of the load will also be constant. So 3, since VA is constant, so is the IA. That is IA equal to IA equal to constant. Second assumption. The fourth assumption is that the resistance, in fact, the stray resistance of that inductance is 0, because we know inductance are some kind of winding around some coil. For sure they have some kind of resistance, but we assume it is so small that it is negligible. We can ignore it. And if we can ignore that, then we get rid of some RL circuits, and rise and fall of the current will be linear, will be ramp wise. So 4, the input inductor has negligible resistance. This makes the inductor current rise and fall ramp wise, means linearly, if a constant voltage is enforced upon it. Okay. So the fourth assumption, and soon we are going to use these 4 in our analysis and make everything much easier. Without them, it's much harder to discuss about this converter. Any question? Any problem with any of this assumption? Is everything clear? So basically, we assume that the output voltage and current of the converter is constant, and the large capacitor, output capacitor C, help us to make such an assumption valid. We also assume the current IL is continuous, never crosses zero, and a large inductor, input inductor L, help us that. We also assume that input inductor L has no resistance, so a pure inductor. Makes everything much easier when it comes to rise and fall of the current. We don't have any RL circuit anymore. It's simply an L, an inductor. If no problem here, I think I can go to the next slide to see what's happened when we are do the switching in this circuit. So let's assume we have some switching scheme here. So we have a time period like this, switching cycle like this. Then assume that we are turn on and turn off the switch like this. So still the switching method is PWM, as you can see. The period, the time cycle is constant, and we play with the pulse width modulation and with the pulse width, and here to here is T on. Let's see how different thing is going to change. When the switch is on, I hate to ask this question, but let me ask again. What is the voltage across the switch? What is the voltage across the switch when switch is on? You said something. Yes. So when it's on, the voltage across it is zero. It's very much principle of the switch. I hope you have learned that after so much insisting on it. What about when the switch is off? When switch is off, the current of the inductor cannot go through the switch. So see, you have this current here. It cannot go through the switch because switch is off. When switch is off, so it goes through the other possible path, which is the diode. So voltage across the diode will be zero. As a result, voltage across the switch, V switch, will be equal to VA. So if here is VA, then we assume that VA is constant, is not changing. So we are going to use it here. But how the voltage across the inductor is changing? When the switch is on, the current prefers to go through the switch. It's a short circuit. Doesn't need to go through any other element. And currents, we know, like the short circuits. So current comes like this and close like this. So during the time on, what will be the voltage across the inductor when the switch is on? Switch is on, the current go like this, I have shown in red. What will the VL during this time? You want to say something? Yes? Here we have VDC. But when the switch is off, then switch gets off. And as we said, the current should go through here. So now the voltage of the switch will be VA because now the diode is conducting, the voltage across is 0. Here we have VA and here we have VDC. So VL during this time will be equal to VDC minus VA. Is it clear to everybody? Is it clear to everyone? I'm sure it's not, but okay. We will soon show that the area, these two areas, should be equal. We will discuss this in more detail in the next slide, that these two areas are equal because VL average is 0. Because in the steady state, if you remember, we said in the DC machines, we ignore the inductance. Inductance in DC, in a steady state, are like a short circuit. No voltage across them. But we will reach to this point soon. Now let's talk about the VL. During this time, during the on time, the first time that G is on, as we said, the voltage across it is VDC. And we know that, so we know VL is equal L di dt. So di over dt is equal to VL over L. And when VL is constant, we will have that ramp, that linear change. So each time, each interval of on and off, we have some linear change. When VL is positive, the slope is positive, the current is increasing. When VL is negative, the slope is negative, IL is decreasing. So if we have Imax here and Imin here, then during the first interval, the voltage is positive across the diode, You just sit in the diagram over it, and the figure over it. So in this interval, current is increasing. Then the voltage across the inductor is negative. The current will decrease. And it repeats. Sorry. We know the slope of this part What is the slope in this part? It is the slope of rising current. We have the equation there. What is the slope of the current? Pardon? This is the meaning of the slope. What will be the value for that? Not VDC. VDC over L. VDC over L. What is the slope for this part? What is the slope for this part? Anyone? What is the voltage across the inductor in this period? Okay, so what will be the slope? Yes. VDC minus VA over L. Thank you. And because the changes are linear, IL average will be simply the average of I max plus I mean I max plus I mean over 2. So here we have the IL average. IL average. Okay. Let's delete this part. Let's go to the current of diode. It's a very interesting one, in fact. So when switch is on, the current of the inductor goes through this circuit, through the switch, and IA also circulate here. The diode is off. So during this time, the ID is 0. What about the time that switch is off? What will be the current of the diode? The switch is off this time. What will be the current this time of the diode? Anyone? Yes, exactly. So here if the I max, here is the I mean, oh no. So it will come like this and then like this, and it repeats itself. So And ID average will be something like this. ID average. And it is equal to IA, the load current. The reason is that the average current of the capacitor should be 0. Otherwise, you will see some change in the voltage of the capacitor. So ID plus ID is equal to IC plus IA. See, the ID is equal to IC plus IA. So ID average is equal to IC average plus IA average. But IC average should be 0 because voltage across the capacitor is constant. So ID is equal to IA average, but this value is IA. We said IA is constant. Okay. When diode is on, for sure voltage across it is 0. I'm not going to ask you this again. But what is voltage when the diode is off? What is the voltage across it? So when the diode is off is when the switch is on. So it means here we have this current. What is the voltage of diode when the switch is on? Anyone? See, the switch is on is like that diode. The point of the other point of diode is connected to the other point of the capacitor. It's like that we have connected the diode to this point. It's on. It's like it is parallel to the capacitor, parallel to the load because the switch is on. What will be the voltage? Minus VA. See the polarity. So minus VA. And if you remember, diode can only tolerate the negative voltage, no positive voltage. So here are the waveforms for a step-up chopper or boost converter. Any question? Everyone is okay with the waveforms? Does it make sense? Okay. Let's continue. So, okay, no problem. Yep, it's okay. So we have this curve, this waveform for the VL, and we said the VL, the inductor, at the steady state work like a short circuit for the DC current. You remember we remove it from the DC machine circuit. So the inductor L acts as a short circuit for DC voltages across it. So it means the average of the voltage across it should be 0. Therefore, the average voltage of VL must be 0. So it means if this point is T on, this point is T, means the area of this part should be equal to area of this part. And the voltages here was VDC and here was VA minus VDC. So let's calculate it. So VL average is equal to 1 over T. It's a periodic function. We can just calculate it over one period, 0 to T dt. It will be equal to 1 over T from 0 to T on, and in this period voltage is VDC dt. So here this integral is the area of positive shade plus 1 over T from T on to T VDC minus VA dt, and here is this integral is the area of negative shade so it will be equal to 1 over T VDC T on plus 1 over T VDC minus VA T minus T on is equal to 0. Any question here? Is it clear? Very simple averaging of this waveform. Any question? No? Everyone is done writing? Okay. Okay, so we calculated, we used those area, shaded area, and we came up with this equation. So let's simplify it more. Minus VDC T on is equal to VDC minus VA T minus T on. So VA will be equal to VDC over 1 minus T on over T. Now we define again duty cycle D as T on over T. Therefore VA will be equal to VDC over 1 minus A, where D is equal to T on over T minus. So why we are excited about this converter? Because D for sure is between 0 and less than 1. VA will be larger than VDC, greater or equal of VDC. So we build a boost converter, stop-up converter. We can get voltages greater than VDC. In fact, theoretically, we can go even to infinity, though it is not possible, as we know. One of the reasons is the switches. We get to that. So, as D approaches 1, VA approaches infinity. The optimum operating condition for the step-up chopper corresponds to the around 0.5, which is means VA over 2 VDC. Can anyone guess what is the main problem? We don't go as much high as we want for the voltage. I just mentioned it, but anyway. Anyone, any idea, any guess, an educated guess? Remember the voltage around the switches we calculated and around the diode? It was VA. So if you get the voltage higher and higher, you never should go beyond the rating of your switch, your diode or your BJT. So if you get the voltage very high, you damage your switches. So they are going to limit you. Let me also write this one. So when the switch and diode are off, should switches stand an off state voltage of VA. That's the problem. We cannot take it very much high VA, and that's why we usually keep around the D equal to half or VA equal to 2 VDC. Okay. Any question here? Everything's clear? Okay, seems so. Let's also calculate the ripple in the current. So this IL, also we name it input current. That makes lots of sense. I think it is clear, but for future reference, if you see sometimes ask you about the input current of a step-up chopper or boost converter, is IL, that we are going to discuss even more about it. It's very much the same. Don't get confused when they talked about the input current instead of IL. So what we are interested to calculate is delta IL, which is equal to Imax minus Imean. And calculating this one is easy. We know the slope of the changes, so we can simply use them. The slope during the on time was VDC over L. So the ripple will be VDC over a slope multiplied by the time to give the ripple during the time on, the change during the time on. So delta IL is equal to VDC over L dt. You may find this equation useful. So the reason was the slope here, slope was VDC over L, and here is T on. We use it to calculate it. We also want to calculate the IL average. So this boost converter is not going to generate or waste any power, ideally. So input power should be equal to output power. Here is input power from the source, and here is output power to the load. So IL average will be equal to VA over VDC IA. So IL average is equal to 1 over 1 minus D IA. The input current is larger than output current. Makes lots of sense. It's almost similar to transformers. If you increase the voltage, you will decrease the current, because we don't generate or waste any power here, at least ideally do not waste any power. So the output power is equal to input current. We increase the voltage of the output, so the current will be lower. Any question? Is it clear? Clear to everyone? Okay. So we may be interested to calculate Imax, Imean, and here we have IL average. So because the changes are linear, we use very similar formula here. Imax is equal to IL average plus, remember this IL here is input current. don't confuse it with what we have done in the half bridge and full bridges there. And half delta IL, so it will be equal to 1 over 1 minus DIA plus VDC over 2L dt. We use these two equations we derived in the previous slide, and I mean is equal to IL average minus half of delta IL will be equal to 1 over 1 minus DIA minus VDC over 2L dt. But you remember one of the conditions we discussed? We said never input current, never the input inductor current, this IL, cross the zero. So I mean should be always greater than 0. So the chopper operates in the continuous mode as long as I mean greater than 0. So let's calculate and see what we have. If I mean greater than or equal to 0, then 1 over 1 minus DIA minus VDC over 2 should be greater than VDC over 2DL over ddt. So IA should be greater than or equal to VDC over 2L 1 minus D dt. We can change the t to 1 over f, so IA should be greater than or equal to VDC 2LF D1 minus D to remain in the continuous mode. Here is the inequalities, the condition we need to satisfy for the continuous mode operation where f is equal 1 over t is the switching frequency. Any question here? Any question? But what happens if we go to the if we don't work in the continuous mode, operate mode? We are going to discontinuous mode. There's no problem with that. Even you can see the cases that they are working in discontinuous mode, but it's not linear and straightforward as continuous. And even we are not going to discuss it in this class. And we usually try to stay in one of these modes, but it's now no big problem and we can operate there. It's not like that if you go to this continuous mode, your switch is going to be burned and nothing work. No, the relation is not as linear and straightforward as we have here. We cannot use the equation that we found for this part there. So let me write some remarks on what we have about the step choppers, step up choppers. So the boundary between between the continuous and the discontinuous mode is determined by setting I min to 0. So this part is for the boundary. Secondly, there is nothing wrong with this continuous mode, and it may eventually happen at low IA. The expression derived, you cannot use the equation we derived for the continuous mode for the discontinuous mode anymore, but the derived for VA is only for the continuous mode, in the discontinuous mode VA will not only depend on D but also on IA and the derived expressions cannot be used any longer. And very finally, step up chopper is an one quadrant chopper as VA and IA can only be positive. V and IA cannot never go negative, so it's only one quadrant chopper, the first quadrant. Even less than 2 quadrant half bridge that we have, it covers less quadrant and only for quarter one there. Okay, change the time here. Let's finish it.